Here we can see a number of radioisotopes, and we have the top group that's produced in a nuclear reactor, and they're produced by taking the parent or the original element and bombarding it with neutrons. As we know, the number of neutrons and the number of protons, when they're relatively even in an element, it's a more stable element. But when you have more neutrons in that element, you create more unstable or radioisotopes that often this neutron breaks down to form something else and give off radiation. We have here cobalt. You can see the half-life's quite high. Iodine, which is used in the thyroid gland, and that's because iodine is naturally taken up by the thyroid. And so when you put radioactive iodine in the body, it can then go into that thyroid gland and give off radiation, which can then be scanned by a gamma camera. Phosphorus, taken up, looked at in treatment of excess blood cells, often to do with bone or bone marrow or blood cell production. Molybdenum is used to generate and produce our technetium, as we saw in the previous video, with a much lower half-life that produces gamma rays, useful for a gamma camera. The second group are those produced in a cyclotron, and there's a video later coming about cyclotrons and what they actually do. This group is the group that are used for PET scanning. So we've got fluorine 18 there, used in FDG, fluorodeoxyglucose, used in the brain because the brain absorbs more glucose. These ones here all produce positrons, which is the positive electron or positive version of an electron, and are used, as I said, in PET scanning, where the positron released interacts with an electron and produces annihilation and two gamma rays, which are identifiable because of the angle that they come out on. So these are all very useful substances, usually added into molecules which are absorbed differently by different organs in the body.